So, let me start the talk with a statutory warning. First, I am going to address the talk to people who have not worked on this topic before. So, often to just illustrate the key ideas, I would just focus on an interesting version of the result, which need not necessarily be the strongest possible version. So, if you just look up the papers that I might refer to, you would find a stronger version that works in extended forms, which I am not going to discuss here. And again, in order to make the talk more intuitive, I will make once or twice some claims which I will just refer to as LFMT, and this stands for literally false, but morally true. And I think this abbreviation should be more popular, like WLOG. Okay. Okay. So, and also I am just going to make the talk self-contained. So, I will just start with a very brief introduction to the area of dynamic algorithms as a whole. So, what is a dynamic algorithm? You can think of it as follows. You have an algorithm for your favorite computational problem. On a given input I, it produces an output O. Now, the input changes slightly by means of some update, and after this update, the algorithm is supposed to come up with the new output. And this keeps happening again and again. The input keeps undergoing a sequence of updates. After each update, the algorithm needs to adjust its output. Now, we say that the update time of an algorithm is just the time taken by it to handle an update, and we want an algorithm with as small update time as possible. Now, if you think of this setting, you will soon realize that there is a naive answer to this question. Just simply run a static algorithm from scratch after each update, and that gives you an update time that is the same as the running time of the static algorithm. But can we do something significantly better than this naive approach? And this is the question that lies at the heart of any dynamic algorithms problem. And you can see that you can ask this question in the context of any computational problem. So, why, if you are, let us say, doing theoretical computer science, why should you care about dynamic algorithms? I will just try to give three brief reasons. One is that this setting is extremely well motivated. So, if you think of Google Maps, it is essentially trying to solve a shortest path problem, but it is basically dynamic shortest path, because the congestions on the roads change over time, and when you are asked a query, you are supposed to return the shortest route between 2 points. Similarly, you can take your favorite social network and suppose you want to run some computation with it. Since the network keeps evolving with time, what you are looking for is a dynamic algorithm. And in general, you can ask this in the context of any big data application. So, the input data is so huge that it is prohibitively expensive to just recompute your solution from scratch after a small change to the input. Okay. The second reason to be excited about dynamic algorithms is that they are often used as subroutines inside fast static algorithms. So, a very simple example here is Dijkstra's algorithm, which uses priority queues as a data structure. And if you think about it, priority queues are nothing but dynamic data structure. And just yesterday, we had this excellent tutorial from Rasmus, which talked about this breakthrough result, max flow in almost linear time. And you would have noticed that a large part of the tutorial was devoted to dynamic graph algorithms. So, if you care about static max flow, you should also care about dynamic graph algorithms a bit. And the third reason is basically you can take any textbook fundamental computational problem and ask what happens to this problem in the dynamic world. And it so happens that despite years and decades of work, the computational status of many such textbook problems like shortest paths, matchings, min cut and so on are still open in the dynamic setting. And once you study these textbook problems, in order to make progress on it, you discover surprising connections between dynamic algorithms and other areas and surprising transfers of techniques between these areas. Now, as the title of the talk suggests, today we are just going to pick the maximum matching problem and study it in the dynamic setting. Okay. So, let me now formally define the dynamic matching problem. So, we all know what a matching is, but let me just quickly recap. We have a graph with n nodes, m edges. A matching is a subset of edges that do not share any common endpoint. So, the red edges in this graph are matching, and we basically want to find a matching with approximately maximum size. So, ideally we would like to get an alpha approximate maximum matching, a matching whose size is within alpha factor of opt. Here opt denotes the size of maximum matching. This is the notation that I will use throughout the talk, and our approximation guarantee I will just treat it to be greater than 1. Now, here is a dynamic matching problem. The input graph is undergoing a sequence of updates, and we have our dynamic algorithm, and it is supposed to maintain a matching in the current graph at all times in some region of the memory. I will call it the output memory. So, each update inserts or deletes an edge in the graph, and after this update the dynamic algorithm does some computation, and after that maybe insert or delete some edges in the solution M it is maintaining. That is it. And what we want to do is minimize both the update time and the approximation ratio. And note that there is a trade off here, because if you do not care about update time at all, you can just maintain a single edge. That is a very bad approximate matching, but your update time will just become constant. On the other hand, if you care about approximation ratio to be 1, after each update you can just recompute from scratch, but then your approximation ratio is small, but update time is very large. So, we want to study this trade off, and throughout this talk when I mention the phrase amortized update time, I just mean this. Amortized update time log n just means you started from an empty graph, then after a sequence of t updates the total time the algorithm has spent to handle them is at most t log n. So, that is the basic preliminaries. Okay. So, what is known about this problem? Well, this is not even a complete list of work that has happened on this problem, let us say in the past 10 or 12 years. So, I have still missed out on a few of the citations. Now, of course, it's beyond the scope in this talk to just describe each of these results, but let me just try to say why are there so many papers studying the dynamic matching problem in recent years. Well, one reason is you can just consider various different trade offs. It is not a one problem, it is basically a collection of problems. So, for instance, you can focus on worst case update times, or you can say you are happy with amortized update time. You can focus on fully dynamic setting or only insertion only or deletion only settings. You can care about the distinction between deterministic and randomized algorithms, weighted versus unweighted graphs, and try to optimize the specific dependence on epsilon and log n in update times. And you can also consider special cases of graphs, special classes of graphs. However, to keep things simple and intuitive, in this talk I will just take the following approach. We care only about the fully dynamic setting, which allows for both insertions and deletions, and we only care about the trade off between update time and approximation ratio. Okay? And I just want to study this trade off ignoring all other distinctions. So, this is the viewpoint I will take in the talk. So, with this perspective, what is the ultimate end goal, the holy grail in this line of research? I would say this, and we right now do not have any clue as to how to answer this question. The question is, can we get 1 plus epsilon approximate dynamic matching in poly log n and 1 over epsilon update time? Now, you might ask, why is this the ultimate goal? I will just give you two answers. One is, in the dynamic setting, an update is just edge insertion or deletion. So, in an n node graph, you can specify an update using log n bits. So, we are just asking for update time that is polynomial in the input size, that is one way to look about this. And the other one is when you have a polylog n update time algorithm for a dynamic graph problem, this implies in a black box manner a near linear time algorithm for the static problem. So, just start with the empty graph and insert the edges one at a time and just feed this sequence of updates to the dynamic algorithm. Okay. So, that is why we say that if we have a polylog update time algorithm, we have matched the static running time. Yeah.
I'm a little worried about the dependence on 1 over epsilon because if the matching size is theta of n, so let us say n over 2 and you output a matching of size n over 2 minus 1, then epsilon is theta of 1 over n, so poly in 1 over epsilon is kind of trivial.
That is a very good point. So, the question was, if we just want to get let us say an additive approximation, maximum matching size is n over 2, we want a matching size of n over 2 minus 1, what can you do there? And this only gives a multiplicative 1 plus epsilon approximation. I will just say one thing, it is known there is a very strong conditional lower bound. It just says that you cannot maintain a one approximate matching in polylog n update time. Now, I need to think a bit, but my hunch is that lower bound would also extend if you just ask for additive one approximation.
If it's n over 2 versus n over 2 minus 1, then epsilon is theta of 1 over n. In the multiplicative sense?
Yes.
Right? Then poly 1 over epsilon will become theta poly in n, which is trivial. So I don't understand. So should the dependence on epsilon on 1 over epsilon be smaller than poly in 1 over epsilon?
Actually, that is a good question. I take your point that if you have an upper bound like this, you can say that I am getting good update time only when epsilon is some small constant. I take your point, but whether it is even possible to get poly log 1 over epsilon update time or there would be a conditional lower bound against that, I am not sure about. My guess is there would be, but I am not 100% sure. But I agree, of course, it will be even more amazing to get poly log 1 over epsilon, but right now we do not even know how to get poly 1 over epsilon. Okay, good question. Thanks. Okay. So, now what is the state of the art? Here is one way to look at this, just look at this chart. The x axis is the approximation ratio, the y axis is the update time. Now, we know that if we care about 1 plus epsilon approximation, we can get n update time, treat epsilon to be a small constant. And this is still non-trivial because the trivial algorithm would be recomputing from scratch, that would give you m number of edges update time. Now, you are getting n. We know how to get 1.5 approximation in root n update time, and we know how to get close to 2 approximation in polylog n update time. So, here in the y axis O tilde 1, this point is just polylog n update time. And there are some interesting trade offs between smooth trade offs between these two ranges, these 2 points. Now, these are just not some isolated data points in this chart. If you are asking what kind of techniques are people using to get these results, there is a very coherent answer to this. 1 plus epsilon approximation, they use a technique which is very standard in dynamic algorithms. I will just term it periodic rebuilding. 1.5 approximation, as Aaron pointed out in his tutorial yesterday, all these algorithms are primarily based on EDCS. And this 2 plus epsilon approximation, they are basically trying to implement the greedy maximal matching algorithm in the dynamic setting. That is why you get 2. Now, this was the state of the art until very recently. Just within the last 1 year, there has been some exciting developments. So, it has been shown that all these 3 data points, none of them probably are optimal. So, there has been very slight improvements to each of these. So, for instance, if you just look at this, it is just saying you get 1.99 approximation in polylog n update time. This data point is saying you can get 1 plus epsilon approximation slightly better than n update time, and so on. However, very intriguingly, all these new results work only for the value version of the problem. And the value version of the problem is you do not maintain an explicit matching, instead you just maintain an estimate of opt, just one value. Okay? And there is a deeper reason why all these new results work only for the value version. That is because all these new results are crucially exploiting sublinear matching algorithms. And Sohail in his next talk would be talking about this in more detail. And in the sublinear world, it is known that you can only report the value if you are asking for sublinear update time. So, that is the main reason. So, what is the plan for the rest of the talk? Yeah.
The way you define it is that you only allow for update time, there is no query time here. But for the applications you talked about, let's say in the static algorithm, you can also have a polylog and query time.
That is true. So, you can actually define a query version of the problem where given a node just report whether it is matched or not, and if yes, return a matched edge.
Or version like that, and then this comment you made about sublinear matching algorithms is not valid, no? Because we have LCAs for matching.
That's a good point. That's a very good point. So, for instance, I was just hiding this under the rug. For this 1 plus epsilon approximation, we can answer that query version of the problem, but it is still weaker than actually maintaining an explicit matching in output memory.
But how do you define maintaining explicit matching in memory? Like, what does that mean? Have you written the matching somewhere in the other algorithms?
Yes. Okay, good. So, now what is the plan for the talk? Let me see, how much time do I have? Roughly 20 minutes? Okay, good. So, I will first just focus on this part 1 plus epsilon approximation in n update time. I will just try to explain how this works, okay? And this is relatively easy. So, I will just present an alternate proof using something called vertex sparsification, and this will be useful later on in the talk. So, vertex sparsification basically just says this: suppose you have a dynamic matching algorithm with some update time u, however, it gives you a good approximation ratio alpha only when opt is large, and when opt is small, it does not give you anything interesting, let us say. Then in a black box manner, you can convert it to a dynamic matching algorithm with update time u times some polylog, and approximation ratio is just 1 plus epsilon times alpha. And the summary here is, when you are thinking about the dynamic matching problem, just pretend that the adversary is ensuring all the time opt is at least n over 1000, and now try to solve the problem. If this is the case, then a 1000 approximation is trivial, right? You just return n over 1000, just think about the value version of the problem, but we care about much more fine grained approximation. Okay. Now, how to achieve this? The argument is actually very simple. I will just give a proof sketch. So, right now in this slide I am not looking at the dynamic setting, I am just describing a random experiment. Okay. We know the value of opt, let us say, partition the node set V uniformly at random into let us say 100 time opt many buckets. So, each node gets thrown into one of these buckets uniformly at random. Now, let G star be the contracted graph with respect to these buckets. So, each bucket is now one node, and let us say only these red edges, crossing edges survive, the blue edges, the internal edges disappear. What can we say about opt in this contracted graph, opt star? We can say two things. One, opt star is at most opt. Why? Because if you have any matching in the contracted graph, it is easy to see that it corresponds to a matching in the original graph. Okay? You just stare at it for 2 minutes, it is easy to figure out. So, this first inequality holds always. And now, I will say that opt equal to opt star with constant probability, and it is basically a balls into beans argument. Why? fix the maximum matching opt in the original graph, how many matched nodes does it have? 2 times opt many matched endpoints it has. So, you have 2 times opt many balls, you are throwing them into 100 opt many bins uniformly at random. With constant probability, all these balls will go to distinct bins. And conditioned on this event, the maximum matching in the original graph would just survive in the contracted graph. Okay? So, and what is the size of the node set? How many buckets it has? 100 times opt many buckets. So, with constant probability, this contracted graph is a good vertex sparsifier. We have preserved the size of the maximum matching, but the number of nodes is now very close to the size of the maximum matching. And now, if you just stare at it for 5 or 10 minutes, you would realize that it just seamlessly extends in the dynamic setting. I will not outline the proof, I will not give the detailed proof, but here is the thing. In the dynamic setting, we do not know opt. So, we just make log many guesses of opt in powers of 1 plus epsilon. For each such guess, we just repeat this experiment polylog n many times to just boost our success probability. So, we have polylog n many instances. On each of these instances, just run this algorithm, initial algorithm that you had, which works only when the input matching size is large, take the best possible answer. That is it. Okay. So, again, just the summary is, we just assume opt is always at least n over 1000. Now, once you have this, here is the dynamic algorithm by Gupta Peng, which gives n update time. It is actually very simple. So, it is just 3 lines of pseudocode. Step 1, it is a dynamic setting, right. So, let us say at the start, at pre-processing, you compute a 1 plus epsilon approximate matching m in the input graph. Step 2, during the next epsilon n updates, you just be as lazy as you can. So, you had computed a matching m, just output the intersection of that initial matching with the edges that are currently present in the graph, and then at the end of this epsilon n updates, go to step 1, again recompute a matching in the current graph and keep doing this. Now, why does this give 1 plus epsilon approximation? The reason is simple. In step 1, you had a 1 plus epsilon approximate matching. In step 2, during epsilon n updates, your opt decreased by at most 1 minus epsilon factor, because each update can reduce by opt by an additive 1. So, at the end of step 2, you still have a good 1 plus epsilon approximation, and that is why it always remains 1 plus epsilon approximation. What is the update time? Step 1, you just run a standard matching algorithm. It runs in n squared time. Step 2 lasts for epsilon n updates. You are not doing anything basically. You are spending constant time per update in step 2. So, your amortized update time is just n squared divided by the length of the number of updates in step 2, which is epsilon n. So, your amortized update time is n, and this is already non-trivial because recomputing from scratch would give you m update time. Now, here is one highlight. This is a very recent result that we have, it is on archive. What we could show was there is actually a 1 plus epsilon approximate matching algorithm that runs in sublinear in n squared time. So, let us say it runs in n to the power 1.99 time. And since this is a sublinear algorithm, we only can estimate mu of opt. So, we can only estimate the value of the opt, but it is fine for the next epsilon n updates. We just return this value as our estimate, everything else remains unchanged, but now our update time just becomes n to the power 1.99 divided by epsilon n. So, it is n to the power, it is better than order n update time. Okay. And if you are interested in exploring this result a bit further, Peter would be presenting a poster precisely on this result later on in the afternoon. So, please go ahead and talk to Peter about the details during the poster. Okay. Now, if we get back to this slide, we understand how this works. I will now just give a very brief overview of these two approximation ratio. how to get this in polylog update time, but here I need to be lot of hand wavy, a bit hand wavy because the algorithms are complicated and I do not have that much time. So, basically as I said, what is happening here is to approximation polylog update time, we are just implementing the greedy algorithm. So, let us say we are just running the greedy algorithm for matching, which will return a maximal matching. So, just recall a matching is maximal if you look at any unmatched edge, at least one of its endpoints are matched. And you can get such a maximal matching as follows, just scan through the edges in any arbitrary order, just take as many edges as you can in your matching as you going through them in this order. Okay? And it is folklore that any maximal matching has approximation ratio at most 2. So, how can we maintain this dynamically? So, suppose we are maintaining a maximal matching, here is a naive algorithm. When an edge gets inserted, what do we need to do? We basically just need to check whether both the endpoints u and v are currently unmatched or not, because if they are unmatched we can just throw them into our matching, the new matching becomes maximal, and this is just constant time. On the other hand, when an edge gets deleted, we just visit its 2 endpoints. If this deleted edge was matched, was present in our matching, we just visit its both endpoints and just check if for each of these endpoints u and v we can rematch it to some free neighbor. So, basically we are just scanning the adjacency lists of u and v, trying to find potential free neighbors of u and v. If yes, we just rematch them. And how much time does it take? We are just scanning the adjacency lists of u and v, right. So, the time taken is proportional to the degrees of u and v, and it is just order n because these degrees can be as large as n. Okay. Now, this maximal matching algorithm has order n update time, but 2 approximation ratio, but this order n update time is really bad. Can we do much better than n? And it is known that we can do, and if you try to just answer this question, you will just end up with 2 different approaches that have been widely exploited in the dynamic matching literature in the past several years. The first approach is randomized greedy and the second approach is fractional matching. I will just briefly describe what randomized greedy is doing. I will not have time to describe the fractional matching based algorithms, but yeah, let us just stick with the first approach. So, the randomized greedy algorithm is basically just this. You take a uniformly random permutation pi of the edges in the graph and just let m pi of g be the output of your greedy maximal matching algorithm when it visits the edges in this random permutation. And now it is known by a sequence of very impressive results that the output of this randomized greedy maximal matching actually can be maintained in polylog n update time. So, although the vanilla maximal matching algorithm which we described has order n update time, this is exponentially faster. Okay. So, since I am running a bit behind on time, I will just keep the intuition, but this is a good fact to know. So, the corollary is we will get to approximate dynamic matching in constant update time with high probability. I will just skip this part. Let us see. So, now in the rest of the talk, I will just briefly sketch this result, this recent result that we had, which obtained 1.99 approximation in polylog update time. And here the motivation is, can we do better than randomized greedy in the dynamic setting? Yes. Can we?
Can you have like the similar result but probability 1?
Sorry, I didn't hear you clearly.
Okay, can you get until node 1 update time but deterministically?
deterministically you can get 2 plus epsilon approximation in O tilde of 1 update time. It is an open question whether you can get even exact 2 approximation in O tilde of 1 update time. Okay, thank you. Okay. Okay, thanks. Yeah, I will wrap up in 10 minutes. So, now this part of the talk is based on this recent paper I had, which is joint work with Peter Kish, Thachapal Saranurak and David Weiss, and Peter and Thachapal are present here. So, at a high level this is just our result, that we get 1.99 approximate dynamic matching in polylog n update time. It works only for the value version of the problem, and independently and concurrently the same result was obtained by Sohail. Okay. So, let me just give you a very brief overview of the techniques, and to keep things simple, just assume the graph is bipartite, adversary is oblivious, update time is amortized, we just want better than 2 approximation. Okay. So, why is it difficult to beat 2 approximation dynamically? You end up with this vertex update barrier, and let me just try to illustrate a very natural approach for getting 1.99 approximation. You will say that I first maintain a maximal matching M1, I know how to do this, it can be done in polylog update time, and then I will just try to augment this maximal matching M1 by a second matching. So, let G prime be the edges crossing between matched and unmatched nodes in M1. Look at this graph, find another large matching highlighted in green here, M prime in this graph, and just try to augment M1 along M prime, and hopefully you get better than 2 approximation. The difficulty here is, if there is an edge update in M1, this leads to vertex updates in G prime. So, an edge update in M1 can change the matched status of a node in G prime in M1, and it means it leads to tons of edge insertions in G prime, and we do not know how to handle vertex updates for dynamic matching. And you can try to just get around this barrier, trying to work various different tricks. It just does not work, and people had tried this for several years, it just does not work. So, the main message behind our result is the following. You just need to observe 3 things. First, that there is a very elegant sublinear algorithm for matching, which I believe Sohail will talk about in his talk just after this. The second one is this vertex sparsification procedure, which was not very widely known within this community until very recently for dynamic matching. And the third is that there exists a semi-streaming algorithm for matching. And once you see these 3 facts, it almost immediately imply our result. And actually with hindsight, the result is so simple that I will just show you 2 memes which just struck me when we first realized that this would work. Okay? The first one is this message, that you just need to know the things that would be useful for you. And the second one is this meme from a movie called Glass Onion. And once you realize that this was a big open question in this topic, and with hindsight the solution becomes so simple, this is really the thought I had in mind. Okay. So, what are the 3 facts? Fact 1, sublinear algorithm. Sohail has a very elegant algorithm from 2 years back, which says that you can obtain a 1 plus epsilon approximate estimate of the size of maximal matching in a graph in n polylog n time. Okay? It is much faster than n square. The second one is this vertex sparsification procedure, which was implicit in
What does that sentence mean? Because maximal matching doesn't have a size, it's like a range.
You can just call it the size of the random order maximal matching. Okay. The second one is this vertex sparsification procedure, which, as I said, it was implicit in previous work, including some work by Safir and others in other settings, but it was not very widely known in the dynamic setting until very recently. And the third one is this semi-streaming algorithm, I will just describe this algorithm, I will skip the analysis for lack of time, but the algorithm is very easy to describe. Think of B as being some large constant, let us say 10 or even let us say 100 or something, and delta is being some small constant 0.01 or 0.001 when you are thinking about this. And here is just this algorithm. In the first pass, you just get a maximal matching M1. In the second pass, you just get a maximal B matching between the matched nodes and unmatched nodes in M1, and let me just precisely define what is going on in here. So, look at this graph G2 with the same node set V, but only consider the edges that are crossing between matched and unmatched nodes in M1. Okay? This is the graph G2. Now, if a node was matched in M1, give it a capacity of 1. If a node is unmatched in M1, give it a capacity of B, and just get a maximal B matching in this graph. M2 is a maximal B matching in this graph. Okay? And now here is the result. Yeah, I will be done. Here is the result, and you might find it good to know for other contexts. If I now just have the value of M1 and M2, and I take a convex combination of these two values, it is just going to be better than 2 approximation to opt. Okay? And we have a better and more refined proof of this fact, but morally this was implicit in quite a few previous work on semi-streaming algorithms. Okay? So, it is not we are not just getting it out of the blue. Now, once you have this fact, let us just combine these three things together. I will just keep the proof outline because of lack of time. What are the implications? Here is a natural strategy, maintain a matching, the maximal matching M1, sorry, what? Yeah, in polylog n update time, we know how to do this, and now we just need to maintain the size of M2, that suffices for our estimate of mu. And now here is how it will work. So, look at this sequence of updates, I will just partition them into phases, each phase will last for epsilon n many updates. Recall fact that opt is always very large, that means within a phase opt drops by at most 1 minus epsilon factor. At the start of a phase, yeah, so this is all that I said right now. At the start of a phase, just compute the size of M2 using this elegant algorithm of Sohail's. We know how to do this in n polylog n time. We only know how to get the size, not M2. Now, mu is this convex combination of the size of M1 and M2 at the start of the phase. We know that mu is better than 2 approximation, just output mu throughout this phase, because we know opt did not drop by more than 1 minus epsilon factor, mu remains 1 plus epsilon approximation throughout the phase, that is it. So, maintain M1 in the background using existing work, at the start of a phase use Sohail's algorithm and just be lazy throughout the phase, that is it. This gives 1.99 approximation. What is the update time? For maintaining M1, we are just spending polylog time, we are good. For computing M2 at the start of the phase, we are spending n polylog n time, and that is the only non-trivial work we are doing, just amortize this work throughout the length of the phase, which is epsilon n. So, update time is n divided by epsilon n, the update time is polylog. That is it. Okay. So, now we are near the end of the talk. What are the open questions? So, just recall, probably about 40-50 papers have been written on dynamic matching in the last 10 or 12 years. Here is a brief summary of the lay of the land. Very recently, in the last 1 year, we have seen new results, which says that these existing data points are probably not the optimal trade-off we can hope to get. But all these new results use sublinear algorithms, and they have this drawback that you cannot explicitly maintain a matching in an output memory as long as you are using sublinear algorithms. And Sohail is going to talk more about sublinear matching algorithms just in a few minutes. So, this points to some very surprising connections between dynamic and sublinear algorithms. I was not aware of this connection until 1 year back. Okay. So, it just seems that if you now want to make progress on dynamic matching, you better be aware of what is going on in sublinear matching as well. Okay. Now, yeah, I already said this. Now, let me mention 2 open questions, which are I think hard open question in the sense that I have no clue how to solve them right now. Okay. It is not that I have any approach or anything. One open question is, can we get 1.99 approximation for the search version of the problem, where you are explicitly maintaining a matching in the output memory in polylog and update time? The existing approach will not work in any case. The second one is, if you just focus on 1 plus epsilon approximate matching, what is the correct answer? The update time we have is n to the power very close to n squared. I mean, can we show a matching conditional lower bounds, or let us say can we have root n update time? Again, I have no clue how to attack that. And I would say that these are 2 of my favorite open questions in this topic right now, and that is it. Thank you.
Question for Sayan.
Is there any reason to believe that there may be some separation between value and the search version of these problems? Like maybe not at like 2 versus 1.99, but
I would say, I do not know for sure, but I would say that there is a non-zero chance that there might be a separation. I won't be surprised, but that itself to me would be a very fascinating result. Yes.
Suppose we consider vertices getting added, which is reasonable in social networks and so on. That can only change the matching size by bounded amount, right? So can some of these algorithms also instrument?
No, actually there is a strong conditional lower bound which says that suppose you just want constant multiplicative approximation, you have a graph, the graph is unchanged, an update is basically turning on or off a vertex, and you just look at the subgraph induced by the on vertex, just let us say even get a constant approximate value to opt, that is it. It is known that you cannot get better than n update time for that question, conditionally.
For any constant approximation?
Yes.
Better than 1?
N. Yeah.
You say 1.99 approximation for your algorithm. You said 1.99 approximation. It seemed like it would be a lot better than that. Is it really such a minor for the 2?
So, sorry Aaron, is your question how much better can it be compared to 1.99?
I just mean in your algorithm that you showed, like you kept saying 1.99. Yeah, but it's better than 1.99,
Yeah.
right?
So, on bipartite graphs, if I remember correctly, we get something like 1.78 or 1.83 on bipartite graphs. On general graphs, we lose a lot more, and it just becomes maybe 1.94 or 1.96. Now, I would say the following. Personally, I would find it very interesting if using a relatively different approach, someone substantially improves, let us say this 1.96 we have for general graphs to let us say 1.8 or 1.7. But I am pretty sure that by fiddling around with the parameters, exactly the bound we are getting, it can be slightly improved. I mean maybe from 1.96 to 1.92, but that would be less interesting. Yeah.
Okay, if not, let's send Sayan.